Okay, let us. I remember that we started to discuss the R matrix structures for the full Toda system. Something like this. If L is R1 L1 plus R2 L2, then trace of LK Lm. Is it done or does it stay as a home task?
No, that was a home task.
Let us discuss it. How to demonstrate the involutivity of spectral invariants of the matrix L if the Poisson bracket has such a form.
Actually, I proved some. I made some. When I tried to prove this problem, I made some mistake. So
It is very good.
I mean, I actually proved like. I'm not sure this is correct, but I tried to sort something like this, which was there's one here. I'm not sure about this problem, but when it comes to this problem, maybe I can try this.
Is there some difference, some important difference?
I'm not quite sure about this.
Let's try firstly this one.
About this one?
Yes, yes.
Okay. Right. So basically, what we wanted to try and what we wanted to show is, let me just specify the terms in here first.
Okay.
So the R1 is in here is like AB. One, so here comes the identity matrix. R2 is CD, E, CD. Sorry, RCD. One, E, CD. Something like this.
Yep.
So the logic goes like, so I was wrote this because in previous task this was actually task 5, and task 3 was about to find the exact form of which is a kind of like a transition operator or something like this. Like, so I was actually put this in this diagram, in this relationship, whether they get the same answers or not.
You see, if you place, if you take
right in here.
Okay.
Sorry, I forgot to mention about.
No, it's okay.
It was kind of tricky, so basic form goes like.
I'm sorry, but you see this statement. It doesn't depend on the form of R matrices.
Yeah, so
it means that the result is more universal.
I realized it's just a kind of properties, rather than just.
So you make more complicated calculation.
Yeah, I mean,
the fact is simpler.
Yes.
And more universal.
I took this problem more complicated, so that's why it took a lot of time to think about how can I prove this or not.
So let's, however, do more general calculation. So to calculate this, we need firstly calculate this. Before taking trace. how to do this. If you know this or this, in fact, the calculation is similar. It's better to do the simple example. How to calculate this? You understand it?
Yes,
In a matrix form, but it's just Poisson bracket of matrix entries from this matrix and matrix from this one.
Right.
And we need to use the Leibniz rule. So here we have the product of two matrices. And it means that we have product of matrix entries of these matrices here. So we have to calculate the Poisson bracket separately for the first and for the second multiplier in this product.
Right. So
I will write it for you, but you will generalize. Okay? L1, LL plus LL, L1. This is the simple way of calculating this. So it's better to write it L like this. And you calculate this Poisson bracket multiplied by this L1 and this Poisson bracket multiplied by this L1. You see, L1 bracket. So this corresponds to this Poisson bracket. And this to this one.
right. Yes.
K and N are powers. Are powers of L?
Here? Yes.
Yes.
Yes, of course.
Yeah, but when we are computing the trace, the K and N are in the shopping, the number of terms.
Of course. Because if not, they're dependent. We are looking for independent Hamiltonians, independent integrals of motion. Is it clear, or you need some explanations?
I got this. Yes.
Okay, now you have to write this one. Maybe let us demonstrate that trace of L square and trace of L is 0. How to do? You have to expand this using this formula. Please.
You can just. So this term can be just replaced by our terms here. So.
Okay. Let us expand all commutators and all brackets.
You mean the values of the commutators in here?
Yes. There is L1 minus L1 R1.
Yes. I'll just expand it. All
Just
the
all.
terms.
Yes. We will see something.
And
There are some cancelling terms.
okay.
Do you see some cancelling terms?
Yes, I can say this term can be cancelled out with this one.
Yeah.
And okay. So this
Okay.
And what about this term?
There,
No, it survives, so it remains in here. And let's say R2. Yeah, this term cancels out with this term.
no.
No, sorry. Yes, this term.
No.
These two terms cancel out? No, right?
Not exactly, but after taking trace, they will cancel.
Yeah.
But what we have? L1 square R1. Okay.
Yeah.
This one and this one.
Right. Maybe maybe you can just expand it first and then use this property, I guess, to show that it is actually 0.
What's the rest? L1 R2 L2 minus L2 R2 L1. This and this, and minus L1 R L2 R2 plus R2 L2 L1. And then we have to take trace on both components. So what we calculated this, and then they take trace, the trace of this. Is it absolutely clear what is this operation?
You mean that the first trace goes to this one and the second trace goes to the second?
Yes. So we are working with M is a matrix N and Cn square. It means that M is M I J K L I J K L. And then we can apply to it trace of M. It is sum of ijkl trace of M ijkl trace of eij trace of ekl. Okay, and it is obviously the sum of I and k, M I K K.
Because these are just the chronicle there.
Yes. I would like to say that it is the same as trace, the global trace of M. If we identify it with the endomorphisms of C square, Cn square. You remember that they interpret such a vector space as a space of endomorphism of the n square dimensional space. And there is a trace function in this, just a character. It is important because it is zero on commutators. So if you have something as a commutator, then this trace is zero. So it is important to know that this trace is a global trace.
Right.
Okay. What happens if we apply this global trace to such an impression?
So you mean that now it's time to take the trace
Yes.
in this
Yeah.
notation?
Yeah.
Now, if you are taking the trace in this formula, maybe you can get this becomes a zero.
Yes, because
Yes.
it's a commutator.
Yes, exactly. And the trace, let me just write down R1. Maybe I think we can use the cyclicity of
Yeah.
the trace
Yeah.
so that these all the terms goes to zero or something. And that's
This is also a commutator, you see? With
no, oh wait. I think that maybe no.
so there is
R2, R2, R1. This term. Wait. Oh, sorry. Yeah, it's not.
But you see, L1, L2 is equal to L1.
Mm.
These are matrices and different tensor components, so they commute. But R acts on both components, so
Right.
so you can
This-
change the order here,
Right.
and it will be this will be also just a commutator. And this you can use the cyclicity
Mhm.
and here, and also use the, and it is also a commutator.
Oh, sorry, I didn't follow. So you mean we can just write down this term into like so L1, L2 equals to L2,
Yes.
L1,
Yes.
and
And this is the commutator
right.
after this change.
Mm-hmm.
And here we can use the cyclicity
Mm-hmm.
as you like. For example, we can,
Yes, yes.
and here L2 on the right,
So they are the same.
they're the same.
Mm-hmm.
Yeah. Can we generalize this calculation to this?
Okay.
Yes.
So, like in the previous, I think we can just was something like. Maybe we can just we can think k equals 2 and m equals 1 in this case. Like this, we can just write R1 first. We can try this way. Like this. R1 k minus 1. There. I'm not sure this is correct or not. But
Yes, yes, absolutely. But k minus, no. You see, the number of such L should be k.
yes.
In your case,
Oh,
it is
sorry,
k plus
it's
1.
K minus 2, and
Yes.
because of that the number of the error.
And it's better to start with the 0.
Right.
out
Okay.
here.
Oh, sorry. Let me just rewrite this. Starting from error 0 is
Yes, very good. With LM. And LK minus 1.
k minus 1. So
K1.
the total number of the
Yeah.
the errors are
L1. L1 power k minus 1. No,
You
no,
mean the
no,
here or
here.
some- Oh, sorry. Yes.
Yep.
Two error
L1 k minus 1.
R1 k minus 1.
Very good. Yeah. No. Without that.
Oh, so that's it, right? So the total number of the
Yeah,
error is
yeah, yeah,
k.
yeah.
Yes. And now it's time to expand this
Mhm.
term, which is now keeping in mind that the number of the error equals to n.
Mhm.
R1 k minus 1, so R2 and minus 1, so that the sum of the number equals that.
Yeah.
And
Too much. Too much.
Right. The second term.
It's a
should
point
be,
to introduce indices.
Huh?
It's a point to introduce indices,
Indices.
which will simplify the calculation.
Oh, right. You mean the expression into the summation or something?
Yeah.
Okay.
I will give you a hint. So it's a sum over, it will be the power of L1 here.
Right.
E from 0 to k minus 1.
Mm-hmm.
0, k minus 1, L1 power I, Lm, L1 power k minus I minus 1.
Right. So we can just write it down here
Mhm.
as a summation.
Now you have to introduce the correct description of this commutator, of this bracket.
0, k minus 1. I think with the same way,
Yes.
maybe we can just
Yes.
write down I R2. Oh, sorry, there should be a R1 I R2 C. K minus 1 R2 was it M minus J minus 1 something.
Very good.
And now I think it's time to use this relation.
Yeah.
So just plugging this in here, which led us to have like this. And I think we have now it's time to expand all terms in
Yes.
here. So
And the next thing to make it separately with this summand and this summand separately, because they
separately,
Yeah.
okay. We can,
they will both cancel.
right. Okay. Then I'll just go with the R1 and L1.
Yeah. Yeah.
So first, let's say it's the sum equals to R1I, R2Z, R1, R1, and we have R1 K minus J, R2 K minus J minus 1, and we have so R1 K minus J in here,
Mm-hmm.
and we can, so since R1, as you mentioned, R1, they are commutative. Maybe
But with commutator, with the opposite, we need it here.
right.
All this commutator.
Mm.
Yeah, you have only product R1, L1.
Oh yeah, I thought that you were just saying that
No, no,
we are
no,
just considering
no,
those one
with the commutator.
or the commutators. Okay.
But the first commutator.
Our first commutator.
Yes.
I'm sorry, sorry. Let's keep that. And
No, the commutator is important. If not, it's not true. Mm-hmm.
right here. So that's the same summation. I'm not sure about whether I can just send R1 into. Okay, that's fine. R1I, R1. No. J, R1 K minus J.
No, K minus I.
Oh, sorry. K minus I.
Mm-hmm.
R2 M minus J minus 1
Uh-huh.
minus R1I R2Z
Mm-hmm.
R R1
Uh-huh.
okay minus 1 R2 M. Oh, sorry, this should be I M minus J minus 1.
Uh-huh. Now, do you remember that they commute?
Yes, like
Yes.
the R1 and
Yes.
R2 are
Yes.
commutative, so we can just write down terms in here.
Uh-huh. And just add
Yes, just
one
add
here.
in here.
Yes.
Yes. Okay, just erase this.
And now we have to remind that we can see the trace, the global trace.
Global trace
Yes.
of.
You see, they can see the global trace. It means that we apply this global trace to this expression,
Right.
and we can use the cyclic property of this global trace.
So you mean, okay, you mean now we're gonna take a trace of this
Yes.
formula. Okay, so then I think.
It means that you can replace this part to this.
Yeah, exactly. So when it comes to taking a trace, so we have trace, we left with summation. Let's skip the summation. R1, and here is a the I number, the R1 has an I number of I. So trace R1K, and when we sum up this two.
No, I don't. My trace is here.
Oh, sorry. Okay, should be here.
Mm-hmm.
So m minus 1.
Mm-hmm.
And for this term, we have I plus 1. So I plus 1, which comes minus R1 R1 K. And J minus 2, minus 1. So basically they're the same.
Yeah.
So we got 0.
Yeah. Do you understand that we will get the same thing with the second commutator?
Yes, now I get it.
You see, it is very simple, and it is true for general Poisson bracket of this type.
Right.
But we need to know that it is a Poisson bracket. Why? So it is not always so Poisson bracket if you just write such an expression with some R1 and R2.
Yeah.
Where we use that it is a Poisson bracket.
In what do you mean by where we can see the brackets in here?
In this calculation, we use that this operation is a
Right.
Poisson bracket.
Yes, to see the kind of algebraic structure in this space.
We use the Leibniz rule. In calculating this, we use that the Leibniz rule is satisfied, so it's not evident for such. Okay, but if it is a Poisson bracket, then these quantities are in involution. Okay, thank you very much. What is your name? Just a moment.
Thank you.
Nochen.
Yes.
Nochen. Nice to meet you. Okay. What else? What was other home tasks from the previous?
The fourth question was like assuming that n is a GLN-Lax operator and the commutative of R times R equals to P and the commutator between P and R2 equals to minus P R1, which is also same as 1.5 P R minus 2 minus R1. The commutator between the 1.5 P and R2 minus R1.
This one?
Yeah.
Okay. It was your home task?
Yeah, that was a.
But I think we have did it in that lecture.
Yes, we have done it some before. Okay, maybe other questions? Are the home tasks?
That's all.
Just one? Which one?
I mean, that's all.
Oh, that's all. Okay. Let us proceed to the new material, to the R matrix depending on the spectral parameter. So I will recall you the Lax operator for the Gaden model, z minus zi. Let us see at this new context of the Lax operator, which depends on some parameter z. So we have demonstrated that the Poisson bracket of such Lax operator is P over z minus u L1 of z plus L2 of u. And your home task is else to demonstrate this home task that to demonstrate that the trace of L of z power k trace z power m of u commute, and you see for all k and m and for all values of parameters. The question was why we are interested in such situation, then all depends on some additional parameter. You see, we get the bigger involutive family of functions. So such traces commute for all values of parameters. So my statement will be that in this situation, it is an integrable system. So the number of independent quantities in this family is just half the dimension of the phase space after reducing to the level subvariety of Casimir functions.
So a trio now is some polynomial in the degree k and n.
Sorry?
Trace
Yeah.
here is a polynomial in the degree k.
Yes, of course, it is a polynomial on phi, on coefficients of phi, but it depends on z. But it's a rational function on z. If you decompose it and if you consider the coefficients of these functions in the serium z, in the decomposition, Laurent decomposition of z, you get some coefficients which are just the functions on the phase space. So the claim here is that this continuous family of integrals produce discrete family of correct dimension of integrals in involution, which allows which substitute an integrable system, Liouville integrable system. One important ingredient we will take in mind is the spectral curve of the Lax operator. Definition. The spectral curve is an algebraic curve defined by the equation, by the characteristic polynomial of L of z.
In complex space or the projection space?
Sorry?
In the projection space or just the complex space?
Let us consider firstly an equation n c square, but it is better to plug it in some rational surface. You see, it's a rational function on z, so there are some poles. You have to treat it accurately, but principally it's some algebraic equation in two variables. So we define some curve. And the geometry, algebraic geometry of this curve is important in integrability properties. So we will discuss it. But now I propose to you to demonstrate. So this will be our task for now. So this characteristic polynomial L of z minus lambda e. So it's a characteristic polynomial of L of z depending on lambda. So it will have some coefficients lambda k e k of z, and this k e I k of z is a rational function on z. You understand that k of z it is of type 1 over z minus zi to power n minus k, some coefficient k I. If we decompose in z equals zi, it has such a principal term. It is 0, then it will have I1 z minus zi n minus k minus 1, etc. So there is all this family of functions a, k, I, k, I, L. So my statement that they commute k, I, m, j, p. How to demonstrate? This is our task for now. Actual task. So the ideological point is that this spectral curve is an integral. This spectral curve is an object. It's an integral of motion. All coefficients which define this equation are integrals of motion. How to demonstrate it?
So we had our Hamiltonian.
We
got the Hamiltonian.
Yes. So suppose we know that this function commute. It will be a true home task. How to demonstrate that all the coefficients of this equation are else integrals of motion, commute with the Hamiltonians.
Is the logic similar to the previous question? We have the tensor product between the RC and RU, and using the trace of the Poisson brackets. I was wondering if the logic is quite similar to the previous question.
Up to me, not similar, but else from this.
Here we're working in an algebraic curve, isn't it? We're working with the determinant has to be equal to 0.
Yes.
I think we can take the Poisson bracket of the determinant, and then since this is linear, you can take the independent Poisson brackets of the y's, and then since this is equal to 0, maybe there is a way to prove that the independent terms has to be each one equal to 0, and then you have the.
Yes, you say something very relevant, but
I don't know, but
could you write?
it's too simple, the idea. I don't know.
Yes, it's very simple and very efficient.
Yeah, it's not,
But it will change the view of the problem. So, yeah, you see, we start by some functions on the spectral parameter,
yeah.
but we finish by by the algebraic curve, which is an integral. But an integral in which sense? In the space of equations, the equation of curves onto variables, our equation doesn't change if we turn on the dynamics of the system. So all the curve is an integral in the bigger space. But the demonstration is very, very close of what you say. So what I propose to consider, we have the family of traces of L of Z of K, just all K and all variable Z. And I proceed to go to the coefficients K of Z. It's another family of functions, but what do you think, how they are related? So here we have K from 1 to N, and here K from 1 to N. How these families of functions are related? If I fix Z, what do you think? If you have just a matrix, the power of traces of a matrix, and the coefficients of the characteristic polynomial of a matrix, how, what can we say? How they are related?
Well, we define it the same way when we work it with it in the previous exercise. AK is the trace of L K. For a fixed C.
If you know traces of powers of L, could we find, can we find coefficients of the characteristic polynomial? So let's just consider matrix A, matrix n by n, and there are functions like, say, I would say jk, trace of ak, and there are coefficients of the characteristic polynomial, and that a lambda e is equal to the sum lambda k ik. Both of this set of functions are spectral invariants of the matrix A. Okay? Spectral invariants, they depend only on the spectrum of the matrix. Do you agree? I would like to say that this set of functions are different bases in the same space of functions. Let us consider the eigenvalues of the matrix A. Lambda I eigenvalues values of A, then jk, just the Newton symmetric polynomial, and k is just the standard symmetric polynomial. K is the sum of what? Of lambda e1, lambda e n minus k, e1 e n minus k. It's a standard symmetric polynomial on Bezout theorem. So the eigenvalues are roots of the characteristic polynomials, and traces are just in Newton symmetric polynomials on the roots of this polynomial. These are two different bases in the space of symmetric polynomials on the eigenvalues. One basis could be expressed in terms of the another basis and vice versa. So the polynomials C and EK is just coincide with C and GK. They define the same space of polynomials. The space of polynomials on the eigenvalues of the matrix I, of the matrix A, or in our case, the matrix L. And it is, it can be generalized to the matrix depending on the parameter Z. It's the same statement that these sets of functions can be expressed one from another. So they are two different functionally independent bases in the same space of functions. And if you know that such functions are in involution, this will be the same for these functions, because they can be expressed one from each other. So this is just another set of functionally independent polynomials in the same functions in the same space. Do you agree?
Yeah, with that.
Yes, you said principally the same things. But this point of view change the way of treating such problem. So now we consider this algebraic curve as a more complex object, which we interpret as an integral of motion. Okay, and it will gives us many important tools, techniques to treat integrable system. So we will say a little bit about separation of variables. So maybe you know the very famous integrable system, which is the description of geodesics on an ellipsoid. It was maybe the first significant, from the algebraic geometry point of view, integrable system, which was solved by the Jacobi map, which is defined in purely algebraic geometrical terms. Okay, but it will be next time. You have home task, and I wish you good continuation.